Acid-catalyzed hydration of alkynes. So an acid-catalyzed hydration of an alkyne, like the acid-catalyzed hydration of an alkene, involves an acid catalyst such as sulfuric acid, water for the hydration, and because alkynes are less reactive than alkenes, we also add in some mercury in the form of mercuric sulfate as an additional catalyst for this reaction. Okay, so what we have is we have our acid catalyst, water is your solvent, and it's also the nucleophile in this reaction. And the mercury sulfate is an additional catalyst. And again, we need that additional catalyst because alkynes are less reactive than alkenes. Okay, so in this reaction, we see the same regiochemistry that we saw for the acid-catalyzed hydration of alkenes. So this is a reaction that follows Markovnikov's rule. So when we add the water across this alkyne, what we will get is we will get a product, and I'm going to number my alkyne for clarity, where the hydrogen is going to add to the least substituted carbon of the alkyne. So that would be carbon 1. So carbon 1 already had a hydrogen, and we are going to add an additional hydrogen there. One of the pi bonds has reacted, leaving one still remaining. And the water, the OH, will end up on the more substituted carbon atom of the alkyne. So this is an addition that is following Markovnikov's rule. So we will say that this is a Markovnikov addition of water. This initial product that we form has an alkene and an alcohol on the same carbon, and this is something that is then known as an ene for alkene, all for alcohol. So this enol is an intermediate in the reaction. And this intermediate is not stable. This will immediately rearrange and undergo what is called a tautomerization. And what will happen in this tautomerization is essentially this double bond is going to move up to give us a ketone. So the ketone is the product of this reaction, and I'm going to add numbers in so we can see where it has added. So the first Markovnikov addition is what tells us that the hydrogen added to the least substituted carbon, the alcohol added to the more substituted carbon. And after the process of tautomerization, we end up with a ketone on carbon 2. So let's focus in and look at the mechanism for this step, for the acid-catalyzed tautomerization. So here we have the enol. And if we are in acid, we are going to see that this molecule will be protonated first. So the proton source we would have if we have water and sulfuric acid is we have H3O+. The alkene is a nucleophile, and it attacks the acidic hydrogen, and then we break the hydrogen-oxygen bond. So we are adding a hydrogen to this end carbon atom. It had 2, now it has 3, so it will be a CH3 group. And once we do this addition, we're taking electrons away from the carbon where the alcohol is, so we have a carbocation there. We have lone pairs of electrons on the alcohol oxygen that can help to resonance stabilize that carbocation. So we can draw a resonance form that now very much looks like the ketone that we see as the above product. And this is how we're moving around the pi bond. So we're using it as a nucleophile when we add a proton. Resonance gives us this carbon-carbon double bond, and a final proton transfer step where we use the solvent, water, to remove that additional hydrogen gives us the ketone product.